Okay, today we're going to be looking at section 6.2, and this is the real applications of normal distribution. So in section 6.1, we talked about the standard normal distribution with a mean of 0 and a standard deviation of 1. If you understand section 6.1, 6.2 should really be a breeze. Where the problems will look harder, but they're really not harder. So let's go ahead and get started so you can see what I'm talking about. Okay, so in this section, we are going to be looking at different methods for working with the normal distribution when it's not standard. That means that either your mean is not 0, the standard deviation is not 1, or in most cases, both of those are going to be different than standard. We have a conversion formula here, and I'm mainly looking at this so that you understand what your calculator is going to be doing for you. Some of you had statistics classes before and maybe use these conversion formulas, and they're fine to continue using, so I'm going to show it both ways. You can kind of decide which one you're going to use. This allows us to standardize the normal distribution so that any values are actually being transformed to z-scores. So you're taking something that's non-standard and you're transforming it back to standard using this conversion formula. So this is just kind of a diagram showing if we start with non-standard, so we have a mean that could be any value, and our standard deviation is not 1, then when we apply this conversion formula to it, we take something non-standard and we transfer it back to standard, and then we can work with it using the principles that we learned in the first section of chapter 6. Okay, so the steps for doing this would be to sketch your normal curve, label the mean and any specific x values, and then shade the region representing the desired probability. So start with that basic thumbnail sketch and label everything. And then for each relevant x value that's a boundary for the shaded region, you're going to use this conversion formula. So if it's one where you have a lower and an upper bound, you'd have to do 2 conversions. If you just have an upper bound or just a lower bound, then you just do 1 conversion. If you notice, it says with many technologies, this step can be skipped. So our calculator actually will allow us to skip this step, and I'll show you how to do that as well. So use your technology. We're not doing tables to find the area of the shaded region, and that's going to be your probability value. So I want to look at an example here. I'm going to show you both ways, one letting the calculator do the work, the conversion, the other kind of showing you how you would do it by hand. If you're used to doing it with the conversion and you want to keep doing it that way, that's fine. So here we have heights of men are normally distributed with a mean of 68.6 inches and a standard deviation of 2.8 inches. Find the percentage of men who are taller than a shower head, which is 72 inches. So first thing we're going to do is we're going to sketch out a normal curve because we're told it's normally distributed. Okay, it has a mean of 68.6. So instead of going in and labeling our mean as 0, now that it's not standard, we're going to label our mean as 68.6. Our standard deviation is 2.8, and these are both measured in inches. So the question asks for the percentage, and percentage and probability are going to be done the same way. So the percentage of men who are taller than a shower head, which is 72 inches. So we want to find the probability that our value is greater than 72 inches. Okay. So if we're going to do this on the calculator and let technology help us, we've still got to set it up. So we're going to look, 72 is here. One reason it's really good to put your mean is so you can know where to place these values. So 72 is going to be on the upper side of our graph. And we want to find the percentage of men who are taller. So that's greater than. So that's going to be this part here. Okay, so we're going to do the normal CDF because we always do that if we're finding percentages or probabilities. Okay, so we're going to do the normal CDF. Our left bound, this was 72, so our left bound is 72, and it's going to infinity, so E99. And this is the difference here. If I put my mean in and I put my standard deviation in, Then my mean, I'm going to put in 68.6, and here I'm going to put in 2.8, and then that's going to give me my answer. So by putting this as not the standard, so normally from last section it would have been 0 and 1, we're actually going to substitute the mean and the standard deviation. So the calculator is actually going to do that conversion for us, and you can see here that that value is 0.1123. So 11.23%. I will say be careful as to the directions, as this one says find the percentage. So when it says that, you do want to carry that additional step and convert it by moving your decimal 2 places. If it doesn't say percentage, then don't convert it to the percentage. Leave it as a probability. So be really careful that you're giving what it's asking for. Okay, so this was letting the calculator do the work for you. I want to go through standardizing this. Okay, so I'm going to go back to our formula here. So we've got Z is X minus mu divided by sigma. So that should be familiar to you because we use that with our Z scores. So if we, let me get back here. Okay, so what we want to do is we want to standardize this 72 because we want to convert this non-standard situation into a standard situation that has a mean of 0 and a standard deviation of 1. To do that, we need to convert this 72 to a standard score. So we're going to look at Z equals X minus mu divided by sigma to standardize that. So my X is 72, my mean is 68.6, and my standard deviation is 2.8. So when I put that in the calculator, I'm going to get 1.21. Okay, so now this is 1.21, and so I'll do the normal CDF from 1.21 to infinity with 0 and 1 as my standard deviation and mean. I'm going to get the same value regardless of whether I do it this way or whether I do it this way. So this first method, that's letting the calculator standardize it for you. This method here, you're doing the standardization and you're bringing everything back to standard normal. So with this one, standardize your value and then go back to your 0 and 1. In either case, you're going to get this answer or something very close to that. Because we do round this number here and then use the rounded answer, there is a chance that your value is going to be slightly off, but not enough for you to miss them. Okay, here are a few helpful hints when you are finding values from known areas. So we are going to turn some around where we have the known area and we trying to find the value. So first of all, always graph. That helps you to visualize and understand. So be sure you're starting with a graph. Be sure to keep track of which ones are z-scores or x values and which ones represent areas. And then always kind of choose the right area on the graph. So if it's talking about the top 10%, that's going to be located on the right. But if it's talking about the bottom 10%, then that's going to be located on the left. Okay, if you have a z-score that's negative, it's going to have to be located on the left. And any of your areas, or which are probabilities, have to be between 0 and 1 because we know probabilities can never be negative. Okay, so here's an example. This one, we are going to be finding a percentage again. So I'm going to read through this with you. A social organization called Tall Clubs International has a requirement that women must be at least 70 inches tall. Given that women have normally distributed heights with a mean of 63.8 inches and a standard deviation of 2.6 inches, find the percentage of women who satisfy that height requirement. Okay, so if we were to sketch this out, which is what I would recommend starting by doing, your mean for the women is 63.8 inches, and my standard deviation is 2.6 inches. I want to find the percentage of women who satisfy the height of being at least 70 inches tall. So I'm going to be looking for greater than 70. So 70 would be over here. So I'm going to be finding this area. So I'm going to do a normal CDF from 70 to infinity. And this time I have a mean of 63.8 and a standard deviation of 2.6. When I put that in, I can see that I'm going to end up with this 0.0087 as the probability that is going to satisfy those that are greater than 70 inches, which means about 0.87% are going to satisfy that height requirement. I mean, which kind of makes sense because if you have a club that's talking about that focuses on tall club international, then they're going to obviously require that people be fairly extremely tall to be a member of it. And so they're only looking at about the top 1% of women that would qualify to be in that. If you were to standardize it, then you would take this 70, subtract the mean, divided by the standard deviation, and you get this as our z-score. And that's what you would put in here using the 0 and 1 as your standard deviation and variance. You do see there's a slight difference here. We had 0.0087. Here we have 0.0085. And that is just because this is a rounded number and not exact. You are going to encounter a slight variation in your values because of that. Okay, here's one. As we go through more of these, I would encourage you to pause the video and try the problems before you look at how we would work them. That's the best way for you to gain understanding with this material. Okay, this one says British Airways and many other airlines have a requirement that a member of a cabin crew must have a height between 62 and 73 inches. Given that men have normally distributed heights with a mean of 69.5 and a standard deviation of 2.4, find the percentage of men who satisfy this height requirement. So I would sketch out my curve here, and then if I look at this, I want to put the mean in the middle with my standard deviation. 62 would be to the left and 73 to the right. So I'm looking to find the probability that X is between 62 and 73. That's what I'm looking to find there. That's the shaded part. So I do the normal CDF of the left bound, right bound, or lower and upper, whichever you prefer. Lower bound, upper bound, mean, and standard deviation, and I get this as my answer here. It asks for percent, so I'm going to convert that to 92.67%, and that's going to be the percentage of the men who satisfy that height requirement. Now, this would be if I were to convert, I would need to actually convert the 62 and the 73. So I would have 62 minus 69.5 over 2.4, and then I would have the 73 minus 69.5 over 2.4. And then these two values here would give me this value and this value to use in the standard normal setup. So you don't have to do both of these. You can do either one. And I feel like most people, just based on like the history of people in my class, most people will choose to do the first one. Most of the ones that'll keep doing the second one are the ones that learned it that way in a previous class. Okay, so moving on, try this one. Okay, so when designing an environment, one common criteria is to use the design that accommodates 95% of the population. What aircraft ceiling height will allow 95% of men to stand without bumping their heads? That is, find the 95th percentile of heights of men. Assume that the heights are normally distributed with a mean of 69.5 and a standard deviation of 2.4. So we start out with our normal curve. So it's important that it tells us somewhere that it is normally distributed. So we know we start with our normal curve. We know that it's the 95th percentile. We're going to start and draw a line here to represent the place that divides our population so that 95% is below that and 5% is above that. So we've got the 0.95 that's to the left of this line that we're trying to find. So here we're looking to find a percentile. So if we're trying to find a percentile is actually a height value. So because of that, this is going to be an inverse norm problem. Typically, we use inverse norms for percentiles, z-scores, or any other X value. That might be IQ scores, it might be blood pressure, it could be any number of things. So any of these, we're going to use an inverse norm to find the answers for our problem. So on this one, we're going to set this up to find this value here that divides the 95th percentile and the 5th percentile. So we'll do inverse norm. This is again the area to the left, so 0.95, and then put in our mean and our standard deviation. So mean and standard deviation, we get 73.4. We want to round this the same as what our mean and standard deviation were given to us as. So they both have 1 decimal place shown. So I'm going to round this to 1 decimal place. If you wanted to do that as a standardized problem, what you would need to do is to do the 0.95 with 0 and 1 and get your 1.645. Then go back to this equation here, except you're going to put your z in here, and you'll know your mean and standard deviation, and you'll solve for the x. So you'll need to cross multiply and solve for the x. You still get 73.4. It's just a little bit longer process than this is. Okay, here's another one to try. Okay, some educators argue that all students are served better if they are separated into groups according to their abilities. Assume that students are to be separated into a group with IQ scores in the bottom 30%, a second group with IQ scores in the middle 40, and then the third group with IQ scores in the top 30. Okay, the Wechsler Adult Intelligence Scale yields an IQ score obtained through a test, and the scores are normally distributed with a mean of 100 and a standard deviation of 15. We want to find the IQ scores that separate the three groups. So I've got a few things going on. We know it's normally distributed, so we start with our normal curve here. And then we want to divide this up so that we have a bottom 30, a middle 40, and a top 30. So we're going to draw two lines here, and we're going to have our bottom 30, and we're going to have our top 30, and then that's going to leave us the 40% in the middle. So we have this, and from here, we know that we're wanting to find IQ scores. So if I'm finding IQ scores, I'm going to have to use the inverse norm to do that. So I'm going to set these up as two separate ones. The first one here, I'm going to do the inverse norm of the 0.3 and my mean and standard deviation. And so that's going to give me this value here, the 92.13. We're going to round that to the nearest whole number simply because our mean and standard deviation were given to us as whole numbers. So that's why we're going to report that as 92. For the second one, I'm going to do the inverse norm. This time, if I'm looking at this line, I need to find the total area going back this direction. So that means I'm going to have to add these two together, the 0.3 and the 0.4 together. So that gives me 0.7. Okay, and so I get 108 when I round it to the nearest whole number. Here are 4 that I'd like for you to try at this point, and then just after you finish trying these, then check your answers on the following slides. Okay, for number 1 here, it says the national average SAT score for verbal and math is 1028. So that's our mean that we're working with. That's our mean that we're working with here. And our standard deviation, it tells us, is 92. It says, what is the 75th percentile? So that's the line that's going to separate the bottom 75% and the top 25%. So from here, I would do the inverse norm, my area to the left, which is 0.75, mean and standard deviation, round it to the nearest whole number because these are whole numbers, and I get 1090. For the second part, what's the probability that a randomly selected score exceeds 1250? So if I'm working on finding probability, that tells me that this is a normal CDF problem. This one was finding a percentile, and that's why it was an inverse norm problem. Okay, so this one was a normal CDF because it was a probability problem. So the probability that its selected score exceeds 1250. So here's 1250. We'll do the normal CDF from 1250 to the E99, and then with the mean and standard deviation, and we get this as our answer. Okay, for the second one, this one is talking about the average number of calories in a 2-ounce chocolate bar is 265, so that's our mean. Suppose that the distribution of calories is approximately normal with a standard deviation of 15. Find the probability that a randomly selected chocolate bar will have between 250 and 275 calories. So this is going to be my lower bound and my upper bound, and then I just have to put in my mean and standard deviation, and that gives me my answer. For the one that's less than 250 calories, we're going to do another normal CDF because, again, that's probability. So negative E99 to 250, and then 2 to 250, and then we have a mean of 265 and a standard deviation of 15, and it gives me this as my probability. Number 3, this one is talking about charitable contributions. Okay, so the average charitable contribution itemized per income tax return in Texas is 850, so that's our mean. Suppose that the distribution of contributions is normal with a standard deviation of 120. So we know it's normally distributed, and we know it has these characteristics here. Find the limits for the middle 40% of the contributions. So if we've got the middle 40%, then we put the 40% here in the middle, and since it's symmetrically here in the middle, then that divides the remaining 60% in half. So that gives me 30% to put on the bottom side and 30% on the top side. So here I'm asked to find the limits for these income tax return charitable contributions. So because it is some kind of X value, it's going to be an inverse norm problem. Okay, so for this, I'm going to do the X sub 1 is going to be the inverse norm. The area to the left of this is the 0.3, and then my mean and standard deviation. Round it to the nearest whole number because these are whole numbers. The X sub 2 is going to be, I'm going to have to add these two together because I'm looking at the area to the left of this line. If I add these two together, I get 0.7, and so I get 913 for that. Okay, and then here's the last one. When designing equipment, one common criteria is to use a design that accommodates 95% of the population. Only 46% of women satisfy the height requirements for U.S. Air Force pilots. What would be the maximum acceptable height of a woman if the requirements were changed to allow the shortest 95% of women to be pilots? That is, find the 95th percentile of heights of women. Assume that the heights of women are normally distributed with a mean of 63.7 and a standard deviation of 2.9. In addition to the maximum allowable height, should there also be a minimum required height? So looking at this, what we have, if we were to draw this out, okay, it says one common criteria is to design that accommodates 95% of the population. What would be the maximum acceptable height? So we're finding height, so that tells me it's going to be an inverse norm problem of a woman if the requirements were changed to allow the shortest 95% of the women to be pilots. So basically we're wanting to find the 95th percentile. So I draw my line so that 95% is below and 5% is above. And it's an X because it's not standard normal. So when it's a Z, it's standard normal. When it's an X, it's not standard normal. We know that for women, the mean is 63.7 inches and the standard deviation is 2.9. So we've got to find this X to meet these characteristics here. So X is going to be the inverse norm of 0.95, comma, 63.7 and 2.9. Okay, so when we put this in our calculator, we're going to get 68.5 inches. We want to be sure that we round this to 1 decimal place because our mean and standard deviation are given to 1 decimal place. So as we said here, 68.5 would be our answer, and it is greater than this mean, so it would be reasonable. And a height requirement, a requirement of a height less than 68.5 inches would allow 95% of the women to be eligible as U.S. Air Force pilots. So we're only excluding the top 5% of women in heights. There should be a minimum height requirement so that the pilots can easily reach all their controls. So it's not trying to be discriminatory here. It's mainly just that there is a limit to the size of the person that can fit in an aircraft cockpit and be able to perform the duties that they need to perform. And so that's why these restrictions need to actually be put on those. Okay, here's a couple for you to practice with. So these are the answers that you should have gotten. The first couple are just standard normal, so normal CDFs. Put in your lower bound, your upper bound, and keep your mean and standard deviation as standard normal. You should get these values. Part D, you're finding a z-value or a z-score, so you're going to do inverse norm. You do start with this area to the right, but if you're trying to find this one, then you're going to need to find the area to the left. So 1 minus that will give us this as the area to the left. So that's what we'll put in here with 0 and 1. It will end up with negative 0.84 as my z-score. Remember, z-scores are to 2 decimal places, and probabilities are to 4 decimal places. Okay, on E here, if you read through it, you'll find that this is your mean and your standard deviation, and you're asked to find maximum and minimum prices. So since I'm looking for prices, this would be an inverse norm problem. So when I set this up, you put the middle 60% in, and that leaves 40% that I've got to split between the two tails of the graph. So if I split that, I get 20% and 20%, or 0.2 and 0.2. So I've got to find this one, this cutoff here, and I've got to find this cutoff here. So this first one, x sub 1, I'm going to find by doing 0.2 because that's my area to the left is 0.2 and my mean and standard deviation. For x sub 2, if I'm looking at this, my area to the left, I've got to combine 0.2 and 0.6 together to get 0.8. And that gives, and then the mean and standard deviation. So here are my, this would be my minimum price and my maximum price. So this particular dealer wants to only focus on the middle 60%. He doesn't really want to cater to the higher end or to the lower end. So the prices he wants to stay between would be $7,288 and $9,224 if he wants to hit that middle 60% of the market there. We do want to round to whole numbers because our mean and standard deviation were given to whole numbers. Okay, that takes us to the end of section 6.2. If you have any questions, please reach out to me, and hope to see you next time.